Here we go. Welcome, everybody. Here is our first lecture for Math 60. I also teach online sections, so these lectures are going to be posted on my online course. If you hear me talking about the online folks, nice to see you. Today, we're going to cover three sections, section 1.1, 1.2, and 1.3. But first, I want to start with two strategies for learning and doing mathematics that I'm going to come back to throughout this course. And I hope you come back to throughout not just this course, but all math courses and whenever you're doing math. The first is building on what you know. So I like to think of math as exploring an unknown landscape. And sometimes when you need to learn math, it seems like you're being told, find your way to get to this point. And you're like, well, I don't know how to get there. But what I'd like you to keep in mind is that all of you have been doing math your whole lives, sometimes formally in class, sometimes informally, and sometimes without even realizing it. If you've ever played a sport and you had to chase down a ball, you're doing math. Whenever you calculate a tip, you're doing math. Buying your groceries, planning your budget. So we all start with a foundation in our mathematical knowledge. And I think you'll see that sometimes when I talk through content, you'll probably think, oh yeah, no, I know that. I've done that. Some of you this topic, some of you this topic. But we all start with a foundation. And learning math is not about learning something brand new. It's about building on your knowledge little by little until eventually your knowledge includes that new piece. And so I'm going to try, when we're learning something new, I'm going to try to make sure we're building on what we already know. And I encourage you, when you're learning something that feels new, to say, what do I know about this already? What do I recognize? What have I done? Can I turn this new idea into something that I've already done? Turn something new into something you've already done. And maybe that means you're comfortable doing that. Maybe it means you feel really good about it. Maybe it means at least you have notes for it, something you have already done. Plus a little extra. Right? The plus a little extra is not the only new learning. Part of the new learning is recognizing I've done a lot of this. But the plus a little extra is the unknown part. And if you're deliberate about expanding toward that, then your territory that you know is growing and you can rely on all that. So that's my first strategy. My second strategy is use the four, I call them, and many people call them representations. It's just the four ways to think about mathematical ideas. Most math classes focus on the symbolic representation, things like numbers and symbols, maybe variables, right? What a lot of us think about when we think about I'm doing math, I'm writing numbers with plus signs, equal signs, variables, solving by hand, things like that. But humans tend to be much more verbal than we are symbolic. There's some people who are just pure symbolic thinkers, and you can build that skill. But most of us come back to a verbal approach, to words, sentences, translate it, into words. And math is not just symbols. Math itself can be represented through words and through verbal ideas. Humans also tend to do really well with pictures, with the visual representations. So pictures, in the context of math, we might use a lot of graphs. If a picture is worth 1,000 words, a picture can also help you understand a complicated idea. And one that's often overlooked, but I think is really important, is just coming back and thinking about math in terms of the numbers, which will often take the form of tables. We're going to list a lot of numbers and we're going to organize them in a table. So these are the four representations, the four main representations that people usually use to think about mathematics. And in addition to learning how to recognize which representation, how to use each representation, it's also an important skill to learn how to go from one representation to another. You can always switch from one representation to another. And some of those representations are going to be more useful for learning and for doing math than others. So a lot of times you're going to hear me when you're working on something and you ask for help, you're going to hear me say something like, well, have you tried the visual representation? Have you graphed it? That's what Desmos is for. Grab Desmos, put it up there and look at it. Or this verbal, how do you pull an equation out of a sentence? Well, just start by making a table and writing down the information you already know. And maybe that will help you. Are you able to see the screen okay?
Thank you.
Yeah. Okay. So these are my two strategies for learning and doing mathematics, and we're going to come back to those over the course of this class. Now we're ready for section 1.1. Addition and subtraction. We're going to do a review or an introduction of these ideas. So let's start with our set of whole numbers. That's 0, 1, 2, 3, 4, etc., on and on forever. If this is review, that's fine. If it's new, that's fine. Addition is combining numbers through counting. And the symbol we use is the plus symbol. So if I take 2 plus 3, and the equal sign is how we write the result. 2 plus 3, to get to that number, I would count 1, 2, and then 3 more. 1, 2, 3. So 1, 2, 3, 4, 5. 2 plus 3 is 5. If we want to add large numbers, large is a hard word because there can be super large numbers, but there can also be like kind of large numbers. The counting doesn't work so well. Like if I want to add 23 plus 54, I don't really want to do all of that counting. So calculators can help you, but generally the way I would recommend it is write them vertically. And you start with the ones column. 3 plus 4 is 7. And then the tens column, 2 plus 5 is 7. Our answer is 77. This works for any size number. Let's do 946 plus 785. So again, I'll stack them vertically, 946, 785, and add them this way. 6 plus 5 is 11, but 11 doesn't really work. I can't cram it in there. So we do something called carrying. Let me write that better. Carrying the tens value. 11 is 10 plus 1. So 6 plus 5, I put the 1 there, and then I bring the tens value up on top. And now when I add all three of these numbers. 1 plus 4 is 5. 5 plus 8 is 13. So again, I have to take the 3 here and put the 1 there. 1 plus 9 is 10. 10 plus 7 is 17. So there's a 7, and then the 1 ends up there. Okay. So addition has some nice properties. Properties are rules that are always followed. So the first property we call the commutative property. I'm writing the word down so you can recognize it when you see it in your book. The commutative property of addition says the order of the numbers doesn't matter for addition. If I want to say 2 plus 3, that equals 5. Well, then 3 plus 2 also equals 5. It doesn't matter what order I put first when I'm doing addition. This helps us when we get into more algebra and we have terms and we want to move terms around. As long as it's the addition, we can move terms around however we want. We can put 2 plus 3 plus 7. If I don't want that 3 there, I could move it to the front. And that can be useful sometimes. That's the commutative. It says the order of the numbers doesn't matter for addition. The other property for addition that's useful is called the associative property of addition. This says the order of operations doesn't matter for pure addition. As long as it's all addition, it doesn't matter which addition we do first. It doesn't matter which addition we do first. So if I want 2 plus 3 plus 7, I could do the 2 plus 3 first, and I get 5 plus 7. And 5 plus 7 is 12. But I could also take the 2 plus 3 plus 7 and do the 3 plus 7 first, which is 2 plus 10, which is also 12. This again becomes useful to us later So I've just got a bunch of things to add up, and I'm not sure where do I start in terms of what addition do I do first. Doesn't matter, whatever's easiest. Generally, what's easiest is working left to right, but it's okay if you work in a different order. And what you'll usually see instead of this brace that I put here is you'll usually see if you want to indicate you're doing something first, you put parentheses around it. Parentheses means do this first. We can quickly get super complicated. I could put 10 different numbers all added together, and then I could switch them around because order of the numbers doesn't matter. I could add them up in all sorts of different arrangements because the order of operations doesn't matter. But I'm just going to show you these examples so we don't get overwhelmed too quickly. Okay. One more. And this is in the book. It's called the identity property of addition. And what this means is zero, the number zero can be added to any number and it does not change the number. Three plus zero, still 3. 19 plus 0, still 19. I could take 5 and I could add 0 to it 3 times, and that's still 5. This turns out to be one of the most useful properties for doing algebra, because when we want to get rid of numbers, we get to turn them into zeros, and then 3 plus 0 equals 3. Okay, those are our rules or our properties of addition. Let's expand now and include subtraction. Taking away one number from another, minus, menos are often the words we use for subtraction. So number lines, this is a visual representation. This is, right, these here, this 3 plus 0 equals 3. That's symbolic. But now I'm going to look at, I'm going to look at subtraction, and I'm going to use a visual representation because subtraction gets a lot more complicated. But if I start here at 0 and I count out to 8, 1, 2, 3, 4, 5, 6, 7, 8, and then I count back 1, 2, 3, I end up at 5. So I've counted 8 and I've counted back 3, and I end up at 5. 8 minus 3 equals 5. Notice that 8 equals 5 plus 3. If I went to 5 and then 3 more, I would get to 8. So if I go to 8 and 3 back, I end up at 5. This is all great, and it was all great for mathematicians throughout history until someone said, well, what if I go forward 4, but then I go back 7. I take away 7. So I have 4, and now I take away 7, and all of a sudden, throughout the course of human history, people had never had to deal with negative numbers before. And then someone said, what if I take away 7 from 4? What if I take away a bigger number from a smaller number? And their heads exploded. And they had to come up with a brand new type of number, which is negative numbers. -3 is what you get when you take 7 away from 4. So now we expand from our whole numbers to what are called the integers, which include negative whole numbers. Integers are the whole numbers plus the negatives of the whole numbers. And that's okay. And then someone came along and said, well, now that I have negative numbers, I should be able to do all sorts of math with them. So what if I want to subtract a negative number? What if I want 10 minus -6? So if we think about our number line, let me put the 0 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's 10. And I want to take away -6, but negatives go this way. And so if I'm taking in the way, I have to take away -1, -2, -3, -4, -5, -6. Taking away a negative number, subtracting a negative number is adding a positive number. 10 minus -6 becomes 10 plus 6, which is 16. Subtracting a negative is adding a positive. Or you could think of 2 negatives make a positive. If we want to subtract big numbers, like let's take, let's see, let's do 92 minus 47. It also helps to stack them. 92, 47, and a negative. 2 minus 7, that gets us into negative territory. So the way I learned it, if you've learned this before, probably the way you learned it is instead of saying 92, I'm going to say it's 80 and 12. All right, so we borrow the tens. We borrow the tens. And now 12 minus 7, that gives me the positive 5. And 8 minus 4 gives me positive 4. This practice is good. This practice is important. A calculator can support you with it. But I do believe in the value of refreshing your arithmetic skills with adding and subtracting large numbers and eventually multiplying large numbers. I don't divide large numbers. That's what calculator is for me. I can, I've done it. I will do it again someday, but generally it's not worth the brain space. But this is. Okay, couple more things. The identity, the identity property of addition, I'm going to call it the zero identity, works for subtraction. Any number minus 0 doesn't change. -5 minus 0, oops, doesn't change. It's also -5. The commutative property this is order of numbers. Actually, let me do the associative one first. The associative property. This is the order of operations. Works for subtraction. So if I have a -2, -9, -4, I could do the -2, -9 first. That's -11. -2 -9 gives me -11. And then I subtract another 4 and I get -15. Let's do a visual representation of that. Here's -2. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there gets me to -11. And I'm going to go 1, 2, 3, 4 more and gets it to -15. Hello.
Hi. I am Yasi.
Hi, Yasi. I've been saying your name incorrectly, but I got it now. Yeah. Give me like 1 minute to wrap this up.
Do it.
Great.
Your life.
Okay. So this is my visual representation. It gets me to -15. But if I preferred, I could do oops, that's a 4. I could do the -9 and the -4 first, which is -13. And that also gets me to -15. Here's my -2. And now I'm just going to go the -13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right there. Also -15. And by some miracle, I got it aligned vertically. So, lucky me. Otherwise, it probably would have been really confusing. The associative property works. The commutative property does not. It does not work for subtraction. Order matters. Uh, 10 minus 3 is 7. 3 minus 10 is -7. No longer the same result. I think that covers addition and subtraction. That covers section 1.1. I'm going to pause the recording. Yes, I'm going to pause the recording and let Yasi introduce themselves.